about abstract algebra, okay? So this is what I would call the ABCs of abstract algebra. So it's more like an overview, okay? And we'll just kind of get from it what we can. Okay, so you've probably all heard of sets. So we have sets. Okay. For lack of a better letter, I'm going to use like L for monoids. G for groups. R for rings. F for fields. Okay. I mean, these are sort of some of the more common, basic okay, let's ignore if the set can be members of itself. Yeah, this will take too long to go through. So we sort of know what a set is, okay? So that's something without an operation, okay? So I guess, and okay, this one monoid has one operation, two operations, okay, and two operations. Okay, so basically, I think you've seen groups. So this has got like identity. So it's got a one identity. It's associative. So all of these are associative. Okay. So it's associative across the board. Yeah. And this has got an identity. Okay. But this one has an inverse. And this might not have an inverse, okay? And a ring is basically two operations where you have one for the one group, so like, and it's commutative. And when it's commutative, you usually call it plus, okay? And the other operation is times, when they distribute. Okay? Does that make sense? So I guess this is kind of a zoomed out thing. So if you're not too sure of the details, it might be good to kind of take this with a grain of salt. Okay, so a field is basically a ring where everything has an inverse. Okay, so can you see? This is basically like it's a group and a monoid, right? So it's an abelian group. Abelian means commutative, so the operation is interchangeable. Okay, plus monoid that distribute with each other, yeah? And a field is basically a ring where everything has an inverse and they commute, okay? So abelian, so it's basically two abelian groups, one distributing over the other, okay? Does that make sense? So some examples of things, so we don't really need examples of sets, but some examples that you might really want to focus on for monoids, like maybe some functions, yeah? So you can compose functions. So you have maybe like the functions on a set. So functions from x to x, okay? So then the operation is composition. You can compose functions, right? And then you have the identity function. Composing functions is associative. So groups, you could have invertible functions, okay? So like bijections. So bijections on a set X. Okay, so that's the difference is that they have an inverse. And we also see the geometry transformations, right? Translations and all this kind of stuff. They all form a group. Okay. Some common examples of rings. Maybe the simplest example of a ring. Or if for abelian groups, okay, if it's a abelian group, you have integers as well, modulo, whatever. But you could probably more think of them as rings, okay? So rings, you have the integers. Yeah. So you have integers modulo n. Okay. And you actually also have matrices, okay? So for example, so the most generic example of a ring is actually a matrix. So we call this matrices over a field, okay? So maybe you can say real matrices, okay? So for example, the 2x2 matrices, yeah? Where the A, B, C, D are real. Okay? So the way you add them is you just add the entries separately, okay? So that makes it a commutative group, okay? Abelian group. And the way you multiply them, it's a bit weirder. But, I mean, there's a rule for it that some of you know and some of you don't, but we'll ignore it. You can multiply it in a way and it distributes over that addition, okay? And so the important thing about the multiplication is that it doesn't commute, okay? So if you do it in a different order, it might not be the same. Okay, so that's what makes it sort of a more generic kind of ring. It might not commute. Okay, but then you also have sort of commutative rings. And a generic commutative ring is like a polynomial ring, okay? Kind of like, well, it's related to polynomial rings. So, for example, you have an integer coefficient polynomial ring, okay? Or you could have a real coefficient polynomial ring, or you could have a complex coefficient polynomial ring, yeah? Okay, and you can have it in multiple variables as well. Okay. In some sense, we really only we particularly care about the ones that are finitely generated. So the ones where you can only have like one or two variables that determine the whole ring. Okay. Okay, and then you have fields. So fields is like the rational numbers, right? The real numbers, complex numbers. Some more weird fields would be like the integers modulo p. So if you take mod p for a prime p, you actually get a field, right? So the thing about being a field is the non-zero elements have inverses. That's like the definition, okay? So that's that's the second group. Like it's the same as a ring, except that under the multiplication, that it becomes a group as well. Okay, so it has an inverse for multiplication. Okay, so notice here you don't have inverse if it's not prime, because if it's mod 6, then 2 times 3 is 0, so you can't ever get that to be equal to 1, no matter how hard you try, right? But if you have it mod 3, you can times everything except for multiples of 3 to get you a remainder 1, okay? Okay. Okay. So all of these are examples of a single set. Okay. With the operations, and when I say two groups, it's really just one set, but you view it in another way to get the other group, and the two groups interact with each other in this distributing way. Okay. You can actually combine these things to form other kind of abstract algebra structures. Okay. So, for example, if you combine together. Okay, so I mean, in this sense, this is just like this other sense is group and monoid of the same thing gives you a ring, right? Two ways of viewing the same thing as a group gives you a field. Okay. But there's a way to view sort of. There's another way to sort of have it. So you can. There's a way to have two things separate. Okay. So you can have a field and an abelian group. Okay. So abelian group means we usually use the plus symbol for the operation because it means it doesn't matter what order you do the operation. Okay. So maybe you can think of like the integers and that kind of stuff as well. Yeah. If you have these put together, you get what's called a vector space. Okay. Where you have an underlying abelian group, okay, and you can scale. What's a vector, right? You can add them and scale them. So this vector space business gives you a way of sort of having the group underneath and having the scalars act on it from the outside. Okay. Okay. So if instead of a field you took a ring and the same abelian group, okay, you would get what's called an R module, okay, a module. You know, we could call this R module to distinguish it from the other rings, or you could call this an F vector space to highlight the field. Okay. So basically the difference between a module and a vector space is the scalars are not coming from a field. So your intuition behind scaling things might not be right, yeah? So a ring is something like this. So when you scale it, it could end up killing it, yeah? So that's kind of weird. We're not really going to go into that, but it's kind of just one of the things. Okay? And if you have a vector space, okay, that you can multiply the vectors, okay? That's called an algebra, okay? So if you have a vector space where you can multiply the elements, so that's basically upgrading this group to a ring, right? Okay, I might have to phone call one of you in a second, okay? So upgrade this to a ring. This is called an algebra, okay? Or if you want to emphasize the vector space, it's called an F algebra, okay? You can actually get an R algebra as well. And yeah. Yeah. Okay. So there's lots of different structures, but they're all essentially kind of they're sort of they're not doing very different things, I guess. They're kind of doing very similar things. So a lot of these things, they're trying to capture the symmetries. Okay, so you can actually you can have a set, and you can have the symmetries on the set, and you can have them act on them. Yeah, so you can realize the symmetries by interacting sort of functions with a set. Yeah. So actually, you can actually combine a lot of these things together. So for example, you can have a set plus a group, and the group acts on the set, and that's called a G set. Okay. It just so happens that all these combinations of G set, monoid set, ring set, kind of can be viewed as modules and algebras, okay? So that's why we don't list all these other ones, okay? And what I want to talk about today, okay, I want to sort of talk about what a vector space is, because I think you've just gotten to the point where you can really learn that, okay? And so to understand what a vector space is, you kind of need to know a bit about fields, okay? And actually, if you understand a bit about vector space, it helps you learn a bit about fields as well, okay? Okay. So some notation for vector space, it might be like V, yeah? Module might be M, algebra could be A, yeah? Okay, do you have any questions about that? So this is meant to be an overview. It's kind of, you might not know what all these things are, even though I think you should be able to know what these definitions are now, because you've seen the groups one a few times. Okay. Yeah.